Okay, you guys, we are going to look at chapters 15.7, which is Le Chatelier's principle. And this is the principle that you were actually exploring when you did your simulation this week. So these ideas should seem very similar to what you practiced in the simulation and the different concepts that you saw. So this should be kind of a wrap up. So Le Chatelier's principle basically says if that a system is at equilibrium and it's disturbed. So in the simulation, you guys were disturbing it by changing the temperature or the pressure or the concentration of one of the reactants or products. The system wants to get back to equilibrium as quickly as it can. And so by changing those different things, basically you're shifting the rates of reaction. They're no longer equal, and the reaction will take some time to get back to equilibrium. So the Haber process is the process of taking nitrogen and hydrogen gas and forming ammonia. We've talked about this process a few times. It's a super common process, and it is used in industry a ton to make ammonia, which is a really awesome fertilizer. Now, the thing about this process is that it's not necessarily like an endothermically favorable process. And so scientists have used the principles of Le Chatelier to make this process happen more effectively and faster. And basically they work to shift this reaction towards the ammonia product when maybe it wouldn't under normal concentrations or under normal situations. So a couple of things that they can do. If H2 is added to the system, the N2 will be consumed and the two reagents will form more NH3. So in this case, we're adding reactant. And since it was already at equilibrium, the system wants to use up that reactant and it's going to shift it to the right towards the products. And that is a way that we can make more ammonia. Okay. So when they do the Haber process, when they're making this ammonia, they use this apparatus here that helps to push that equilibrium to the right. And one of the ways that it does it by actually removing ammonia from the system. So if we've got our N2 and our H2 and we're at equilibrium, but we want to make more of this NH3, if we remove product, the system wants to work to fill back in that blank. And so what happens is, again, the equilibrium is shifted towards the right to fill back in that product that was taken out of the system. So Le Chatelier's principle basically says is if a system is already at equilibrium, the first effect that we can have is on concentration. So the concentration of any substance is increased. The system acts to consume some of that substance. So if you add reactant, it uses up the reactant and makes more product. If you add product, it's going to use up that product to make more reactant. The concentration of any substance is decreased. The system wants to produce some of that or fill it back in. So if we decrease, it's going to try and produce that. So if we get rid of some of the reactant, the product will react to form more reactant. So when we're talking about Le Chatelier's principle, there's going to be questions posed around how can you shift it to the right or shift it to the left, just like in that simulation that you guys did. So you have worked a ton with Le Chatelier already. You just didn't know that that was called Le Chatelier's principle. So the second effect that you guys looked at was volume and pressure. So in the simulation, we were controlling the pressure, but what that did was change the volume of our container. So when we talk about this, we can talk about either increasing or decreasing the volume, which changes our pressure, or increasing or decreasing the pressure, which changes our volume. So if you reduce the volume of a gaseous equilibrium mixture, the system wants to shift to reduce the moles of gas. And so we saw in our reactions, if we're going from, let's say, the Haber process again. So we've got NH3 like this, our Haber process. On this side, we have 4 moles of gas. And on this side, we only have 2 moles of gas. So if we increase the pressure which decreases the volume. We know that that is an inverse or indirect relationship. If there's less room, it's going to move it towards the side that has less moles. If we decrease the pressure, meaning we're going to make more room, a larger volume, it wants to fill up that volume. And so it would move towards the side that has more moles, or the reactants in this case. The final one is changes in temperature. And so this has to do with whether a system is endothermic or exothermic. So if our delta H is greater than 0, it's going to be endothermic. So when we look at this reaction here, if you add heat, the reaction is going to shift right to increase the blue. So this side is pink and this side is blue in color. So at equilibrium, you get this kind of nice purple color, but we can change the color by changing the heat. And that tells us something about the reaction. So if you add heat, the reaction shifts to increase the blue. So if we add heat, it moves this way. If you remove heat, it shifts to the left. So if we go this way to remove heat, so basically what we can see is that depending on what we do, we can decide if it's an endothermic or an exothermic. So if you add heat to the system is going to work to get rid of that heat. So when you add heat, if it moves to the right, like we said here, that means that heat is a reactant. So if heat's a reactant, that's an endothermic process. Let's just double check that. If you remove heat, the reaction would look to replace it, and it would move towards the reactants, again, because heat is a reactant. Okay, so let's kind of put that together. So the effects on temperature changes. Remember that our equilibrium constant values are temperature dependent, meaning that you would have a different Kc value for each temperature. So when the temperature of a system is increased, the system reacts as if we added a reactant to an endothermic process or a product to an exothermic. So the equilibrium shifts in the direction that consumes the excess reactant or product that kind of uses up that heat or puts heat back into the system. Okay, so let's consider this equilibrium and let's look at these ideas here. So I'm going to do a little bit of labeling first that will hopefully help us. So in the reactants, I see 1 mole of gas. And in the products, I see 2 moles of gas. Okay. We're also given a delta H value that's positive. So I know that this is an endothermic reaction, which means that heat had to be added to the system. So in this case, heat is a reactant. Okay, so which direction will the equilibrium shift when? So part A says we add N2O4. So if we add the N2O4, it wants to use that up, which means that it's going to be shifted towards the products, which is to the right. Okay. If we remove NO2, it wants to fill that back in. So again, it's going to shift it towards the products, which is to the right. Okay. The pressure is increased by addition of N2. So in this example, the N2 is not a reactant or a product. So it's being put in there and it's only changing the pressure. So if we increase the pressure of the whole system wants to get back to that equilibrium. So we're going to move towards the side that has the lower number of moles of gas. So this is going to push us to the reactants, which is to the left. Okay. Next one, the volume is increased. So that means there's more space, which ultimately means less pressure. And so the reaction wants to fill that extra space, increase that pressure back to where it was. And so it's going to move to the products because there are more moles of product. And then finally, the last one, the temperature is decreased. So when we decrease the temperature, it's like removing some of the reactant. And so the system wants to move to fill back in that reactant. And so it is going to go to the reactants, which is the left. So your book has a lot more information on Le Chatelier's, and if you haven't finished the simulation yet, make sure that you do that and you get to kind of play around with these theories.